Okay, so this is the third homework set, and the first problem, which was number 2, is talking about a bike with 2 sets of gears, having 3 gears on the front, 7 gears on the back, and in the problem it says that the customer thinks there are 10 gears possible. He's adding them up. And of course that's wrong because it's not as if you're choosing each gear separately, right? For every front gear choice, you choose a back gear. They're a combination, right? And we know that for each choice of front gear, there's going to be the same number, i.e. 7 choices for the rear gear. Therefore, the counting principle applies, and we can say the total number of gear combinations is 3 times 7, or 21. Okay, in the second problem, number 3, we're looking at a shampoo bottle, and it has different characteristics, right? It can have different colored lids, different colored bottles, different colored prints for the label. And we're assuming here that there's the same number of choices for any particular characteristic given any choice of the other characteristics. Okay? And so in that case, again, the counting principle applies. And so since we have 4 colored lids, 5 colored bottles, 2 colored prints for the label, we multiply them, getting 40 total different types of shampoo bottles that are possible. Okay, for number 6, we're looking at area codes. And what we know is we know that for any one area code, the total number of possible phone numbers is 10 to the 7th. But we're going to assume that every digit, whether it's the first or the last, has the same number of choices. It can all be 0 or 9. That's debatable. I don't know if you could have 0, 0, 0, 0, 0, 0, 0, but we're going to assume that you can, okay? And what we know is we know that there are 5 toll-free area codes, and for each of them, we have the same number of phone numbers. So again, we apply the counting principle a second time, and we get the total number of possible toll-free numbers is 5 times 10 to the 7th, which when you expand that ends up being 50 million. Okay, problem 9 is an interesting problem. We're talking about a byte combination lock, and we're told that that lock has 4 digits, and each digit can be a number from 0 to 20. So we have 21 choices for each digit. And we know how bicycle locks work, right? We can choose the same number of possible numbers for any digit, regardless of how the other ones are chosen, right? So again, the counting principle comes into play, and so the total number of combinations will be 21 for the first digit, times 21 for the second, times 21 for the third, times 21 for the fourth, giving us 21 to the 4th power, and that ends up being 194,481 possible combinations. Now we know that each sequence of those 4 digits is going to be one outcome, okay? And so we're looking at the probability that the specific combination 1, 2, 3, 4 opens the lock. Now, when we're talking about the probability of an event, we're assuming that it happened. It's really important to understand that, okay? And so since it happened, how many ways could it happen? Well, there's only one favorable outcome, right? It can only happen with the one outcome, 1, 2, 3, 4. And we figured out earlier what the total number of outcomes were. So the favorable over the unfavorable gives us 1 over 194,481. And I'm going to leave it that way. You could put that into a decimal form, but it's a really kind of a nasty looking small number, okay? I'm just going to leave it like that. Now suppose we try 50 combinations, and we want to know the probability that one of the 50 opens the lock. Again, you want to remember that when we're talking about an event occurring, we're assuming that it happened. So how many different ways could it happen? How many favorable outcomes? Well, there's 50, right? We try 50 combinations, we could win 50 different ways. So that probability that one of the 50 is going to open the lock is the number of favorable outcomes, which is 50, divided by the total number of outcomes, which is 194,481. And And again, since that's a very small number, I'm not going to bother putting that in decimal form. Now 31 through 35 are dealing with card problems. And so in 31, we're told that we draw the first card from the deck and we return it. Okay? And we want the probability that we draw a 10 on the first draw and a jack on the second. So if we look at the number of favorable outcomes, we're assuming that we drew a 10 and we drew a jack. The number of ways we could draw a 10 on the first draw is 4 ways, right? We have a 10 of clubs, spades, hearts, and diamonds. And then the number of ways we could draw a jack is also 4, okay? So the total number of outcomes that are favorable are 4 times 4 is 16. The total number of outcomes, well, how many ways could I draw the cards, period? Well, there's 51 choices for the first card. And since I returned the first card, on the second draw, there's also 52 choices. So the probability of a 10, then a jack, is 16 over 52 squared, which ends up being 1 over 169. Okay, in 33, we're doing the same sort of thing. We're drawing the first card, noting what it is, then putting it back in the deck. And now we want to look at the probability that we drew a club first and then a diamond. Well, notice that the total number of outcomes hasn't changed, right? The same argument can convince you that the total number of outcomes is 52 squared. And there are 13 cards of each suit, right? So the number of ways that I could draw a club on the first draw is 13. And since I knew I drew a diamond on the second draw, the number of ways I could draw that diamond is 13. So the number of favorable outcomes is 13 squared. When I compute the probability, I get 1 over 4. And since that's an easy number to put in decimal form, it's just 25%. Okay. Last problem. Now here, we're not replacing the first cards. That's important, right? And I want to know the probability that I drew a diamond on the first draw and a diamond on the second. So when I look at the favorable outcomes, since I knew I drew a diamond on the first draw, there's 13 ways I could draw that diamond, right? Now I'm going to draw a diamond on the second draw, but I didn't replace the first diamond that I already drew on the first draw. So there's only 12 possible diamonds left, right? So here, I'm going to have 13 times 12. That's going to be my number of favorable outcomes. Okay? Now, total number of outcomes, well, I could choose 52 cards on the first draw. But then because I didn't put that first card drawn back, there's only 51 to choose in the second draw, and that's going to be 52 times 51. And if you work that all out, you end up getting 1 over 17. And that's it for this problem set.